It's my pleasure to introduce you our today's speaker, Dr. Elena Anashkina, actually Doctor of Science habilitation. She recently defended her doctoral thesis. She's working in the Institute of Applied Physics of the Russian Academy of Sciences in Nizhny Novgorod, not too far away from us. And today she will talk about nonlinear and laser effects in optical microresonators made of different glasses. So colleagues, in case if you have any questions, please either raise your hand and then you will have a chance to ask by voice. You may also type the question in the chat, but if you're asking by voice, please make sure not to interrupt the speaker in the middle of the sentence. So Elena, please, you're welcome. The stage is yours.
Thank you very much for introduction. Hello, dear colleagues. Thank you very much for the opportunity to present my talk at this seminar. It's very pleasure for me, although it's unusual to have a seminar in English in a Russian organization. My talk is about glass microresonator. This is glass ball, glass sphere, but not micro. But further, I'll talk about the similar device, but very, very small, with a size not 10 centimeters, but about 100 of microns. Now I'll share my screen. Okay. And my talk. Here is the outline of my talk. It's organized as follows. First, there will be a fairly detailed introduction. After that, I'll present our team's results on silica glass microresonators, then on chalcogenide microresonators, and finally on tellurite ones. Let me remind general facts about whispering gallery modes. The concept of whispering gallery arose in the late 19th century regarding to the propagation of acoustic waves in galleries along the round perimeter. The most famous example of such unconventional phenomena related to the physical explanation for this phenomena was proposed by Rayleigh, and it relied on the acoustic ray interpretation involving multiple internal reflections along the inner periphery of the gallery. Later, Rayleigh improved his theory and proposed a more accurate formalism based on acoustic waves. The similar effect can be observed in the optical domain. The dielectric resonator with whispering gallery mode can trap photons by total internal reflection. The first theoretical analysis of optical resonator with whispering gallery mode based on Maxwell's equations was demonstrated by me and Debye. Since then, remarkable contributions have been provided to achieve a quasi-complete understanding of these resonators, at least in the linear approximation. But in the study of nonlinear properties of such resonators, surprises will arise. Optical microresonators with whispering gallery modes play an extremely important role in modern optics and photonics. Microresonators based on dielectric materials provide unique capabilities for controlling fundamental properties of coherent light. They have a huge Q factors and large nonlinearity due to extremely small motor volume, which make it possible to nonlinear effects at very low pump powers. Microresonators are attractive for various applications, including sensing and biosensing, optical filtering and switching, frequency stabilization, and so on. In microresonators, it is possible to generate optical frequency comp, which are periodic trains of ultrashort pulses with equidistantly spaced spectral lines. Generation of optical frequency comps OFC in microresonators was demonstrated for the first time in 2007 by Pascal de Haye and co-authors. using COMS expands the application range of microresonators in telecommunication, dual comp spectroscopy, optical atomic clock, ultra-fast optical ranging, and in many other areas. The whispering gallery modes and eigenfrequency of an ideal sphere can be found analytically as solution of Maxwell's equation with boundary conditions corresponding to the interface between the bulk resonator and surrounding medium, which is often area. The expressions for fields are very cumbersome and not given here, but may be found, for example, in the paper by Raevsky. The solutions divided by two classes, transverse electric TE and transverse magnetic TM modes. The whispering gallery mode is characterized by three indices. Q is the radial indices, M is the azimuth indexes, and L is the polar index. The examples of calculated fields are shown here. For the fundamental mode, Q is equal to 1 and L is equal to M. The fundamental mode is localized near the surface and has the smallest mode volume, so the highest nonlinear coefficient. To excite a microresonator, one should use as a rule a narrow line continuous wave laser, since a high Q resonance is very narrow. There are different ways to couple pump light into a microresonator. We use a fiber taper with a diameter of about 1/3 micron made of a standard telecommunication fiber. The method is based on exchange the energy between an evanescent fields of a fiber taper and whispering gallery mode of a sphere. A microresonator with whispering gallery modes is simultaneously a gain medium and a cavity for Raman, Brilluen, or rare earth ion-doped microlasers. Broadband nonlinear optical transformation of low power continuous wave pump are effectively implemented due to the action of Kerr and Raman nonlinearities, including the generation of optical frequency comps. Silica microspheres can be produced in an easy way by melting the end of a standard telecom fiber, and observed nonlinear effects in them in silica resonators can be described by the Lugiato-Lefever equation as for other types of microresonator. So, silica microspheres are a convenient platform for studying nonlinear phenomena and demonstrating concepts. Such microresonators can be pumped by standard telecom companies, and for the studying, telecom equipment can be used. But the use of new materials such as chalcogenide and tellurite glasses with outstanding optical properties allows expanding the capability of microresonators. Our team studies microresonators based on different glasses, including standard silica, as well as highly nonlinear chalcogenide and tellurite ones. Chalcogenide glasses consisting of one or more chalcogens in conjunction with electropositive element are very promising materials for use in various photonic devices, including whispering gallery mode resonators.
Elena, sorry for interrupting. There is a question from the audience. Okay. Why the spheres are used but not the rings? Because it looks like all the field is concentrated on the peripheral.
Thank you. Because we can do microspheres because we have method and technology, and we started working on this direction only in 2019, only 3 years ago, and we think about ring cheap microresonators, but this will be the next stage, the next step in our studies. Here we use non-standard glasses, and there will be some advantages in them. For example, chalcogenide ones allows operating in the mid-infrared. We have not experiments by now in the mid-infrared, but we are planning to do this, using chips and rings requires more complex technology, and now we have such devices.
Right, thank you. And another question from myself, actually. So what is the typical distance between this optical fiber, which you are using for excitation, the modes of the sphere, and the sphere itself? Just the order of magnitude. Is it just few microns?
The distance may be from 0, then they touched, and from to about 1 micron, no, maybe 2 micron maximum value. Okay,
and I see another question from Michail. Misha, please.
Thank you, Max. Thank you, Elena. Elena, can you a simple question? So when you dope with glass with chalcogenide or tellurite, so the refractive index, not the nonlinear but the linear part, how does it change in the range of operation?
Okay, we use chalcogenide fibers with linear refractive index is about 2.3, 2.5. It's higher than for silica 1.5, but lower than for silicon glass. And for tellurite, linear refractive index is about 2. But nonlinear refractive indexes for such glasses are higher. Chalcogenide glasses have nonlinear refractive indexes 2-3 orders of magnitude higher compared to silicon, and tellurite glasses have nonlinear indexes 20-30 times higher than for silicon.
And when you write that it's transparency range and that it's up to some 8,
it depends on composition.
Yeah. Will you show any absorption spectrum in the following? Will there be any absorption spectrum of these materials lately?
Here.
If not, then I'll ask the question. So when you say the transparency range is up to some microns, but I see red and yellow glass that basically
blue border is about for chalcogenide from 1 micron, or maybe from 500 of nanometers, depend on the composition. I can't demonstrate blue boundary, maybe 1 micron, and they demonstrate larger glass, and after that they decreased very sharply. Of course, there may be different peaks corresponding to absorption of such gases in atmospheric, but it's details. Okay. Okay, I'll continue. Chalcogenide glasses have a very low phonon energy compared to silicon, and tellurite have the average value. Tellurite glasses based on tellurium dioxide are transparent up to 5-6 microns, and the advantage that they have very high solubility for rare earth ions, so they can be easily doped with rare earth ions for obtaining laser generation in the range of 1-3 microns. However, I should note that chalcogenide and tellurite glasses are characterized by a low glass transition temperature, which is much lower than for silica glass. Therefore, many standard technologies are not applicable for them. And the next important issue concerns dispersion. Their dispersion wavelength is beyond 2 microns for tellurite glasses and is beyond 4.5 microns for chalcogenide glasses. At shorter wavelengths, the dispersion is normal. Dispersion is a very important factor for the implementation of nonlinear optical effects. And often, many interesting regimes of homogeneization require anomalous dispersion, which is a problem for these soft glasses. However, dispersion is practically unimportant for Raman generation, Brillen generation, and laser generation. So these effects are easier achievable. Our team.
Elena, sorry for interrupting. When we speak about dispersion, do we mean the dispersion of the linear refractive index or
linear dispersion?
Because the dispersion of this nonlinear part is like not super important in this context.
It is linear dispersion is important when we speak about Kerr-Raman frequency combi generation in such devices.
Thanks.
Okay, our team started working on the microresonators in 2019. Until the time, these topics of microresonators had not been studied at our institute. We have created a fairly universal experimental setup for the investigation of nonlinear optical and laser effects in silica and non-silica microspheres. Developed theoretical module to describe the corresponding effects and obtained some interesting results. This table demonstrates what effects we observed and investigated in microspheres based on different glasses. Further, I'll present several of these effects. But before that, I'll briefly talk about the microresonators themselves. To produce microresonators, we use a method based on melting the end of a glass fiber with formation of sphere under the action of surface tension forces. Here you can see the example of manufactured silicon, chalcogenide, and tellurite microspheres. We used commercially silica and chalcogenide fibers, but tellurite fibers were specially produced at the Institute of Chemistry of High Purity Substances. We measure their Q factors by the dynamic resonance scanning method. Then the pump laser frequency is swept linearly and resonance dip is recorded using an oscilloscope. The typical Q factors are given here. And an example of measured data and corresponding Lorentz fit for this tellurite microsphere is shown here. And now let's move on the results obtained in.
Elena, I'm sorry, just for some understanding, what is the spectral distance between two modes? So I see the width was around like 10 megahertz. So what's the distance between the modes?
Okay, free spectral range for fundamental modes for such resonator, for example, for this is about 600 of terahertz, but there are not only fundamental modes, there are a lot of higher order modes from different families. And now I can show this is an example of a full scan by our laser for tellurite microsphere. You can see that there are more than 80 resonance in the 120 gigahertz range.
Thank you.
Okay. Let's moving on effects in silica microspheres. Before investigating nonlinear dynamics of the resonator radiation, it was necessary to calculate several parameters of a microsphere, including a free spectral range and dispersion. The eigenfrequencies of the whispering gallery mode resonators can be found numerically by solving the characteristic equation, which is obtained on the basis of Maxwell equation with allowance for boundary condition. The details of obtaining this equation can be found, for example, in the paper by Raevsky. The meaning of the symbols in the equation is listed here. We numerically solved this characteristic equation for a fundamental mode family. The iterative homemade algorithm was implemented with allowance for silica glass dispersion described by a standard Selmayr formula. After obtaining the eigenfrequencies, we calculated the dispersion as a function of frequency. Note that total microresonator dispersion depends on material dispersion and geometrical waveguide contributions. So dispersion differs for microspheres with different diameters as plotted here. It is very interesting to study the nonlinear dynamics when the pump wavelength is close to the zero dispersion wavelength. We used C-band pump laser about 1.55 microns. So we chose a microsphere with zero dispersion wavelength near 1.55 microns. To analyze the dynamics of optical microresonator fields, we used the generalized Lugiato-Lefever equation. With terms describe evolution of intracavity field, losses, deteriorating, dispersion, Kerr and Raman nonlinearities, and continuous wave pump. For the Raman response function, the standard approximation is used. We used a homemade software based on the common split-step Fourier method. The basis of the method is described in the Agrawal's book. And here we studied Kerr-Raman combos in silica microsphere pumped near zero dispersion wavelengths. The experimental scheme is shown here. The microsphere was pumped by a continuous wave laser widely tunable in C-band. Coupling of pump light and outcoupling of the generated comb was arranged with a fiber taper. The nonlinear dynamic of the intracavity field leading to comb formation was simulated numerically in the framework of Lugiato-Lefever equation with allowance for Raman response. FR is equal to 0.18 and especially without this effect, purposely without Raman response when FR is equal to 0. The experimental spectra in comparison with simulated shown here. Vertical dashed line responds to zero dispersion wavelengths. The Stokes spectral components obtained due to multi-mode Raman generation are labeled by S, and the anti-Stokes components obtained due to forward mixing of the pump light with this Stokes component are labeled AS. First, we set pump wavelengths in a normal dispersion region and obtained multi-mode Raman lasing in the U-band in the absence of Kerr OFC near the pump. The same spectrum was obtained numerically. The calculated phase matching condition for the anti-Stokes signal wasn't satisfied. Therefore, the anti-Stokes signal wasn't generated here. Then we switched off the Raman response in simulation, and the Stokes wave vanished as expected, and only pump wavelengths remained. Next, we set a pump wavelengths near the zero dispersion wavelength and observed three spectrally separated OFC near the pump, Stokes, and anti-Stokes. The experimental and corresponding numerical spectrum are in good agreement. When we set FR is equal to 0, the Stokes and anti-Stokes components were not observed. Therefore, the Kerr near the pump was absent for FR is equal to 0, which may be also explained by the non-zero Raman gain at small frequencies. Further, we set pump wavelengths in the range of low anomalous dispersion. The experimental spectrum with a width of 270 nanometers covering the E, S, C, L, and U bands, and further up to 1.7 microns is here. There are pronounced humps between pump and Stokes here, and between pump and anti-Stokes here. They are due to four-wave mixing. When we switch off Raman response, we obtained these humps here. And further, for a detailed explanation, we produced we conducted some numerical simulation, and here you can see the transitions between optical frequency comp regimes from the results actual for previous slide. Note that spectral envelope is plotted and individual comp lines are not resolved here, and the pump wavelengths change in steps corresponding to FSR. When the pump wavelengths in the normal dispersion range, wavelength tunable multimode Raman lacing is achieved by tuning pump wavelengths. In the slightly anomalous dispersion range, the humps corresponding only to four-wave mixing overlap with Stokes and anti-Stokes humps. The fact that this is not broadening of Stokes comp is demonstrated here, that there are components due to four-wave mixing, but there are no Raman and anti-Stokes components. Further, we studied the case when the pump wavelength was in the normal dispersion range. We obtained a very interesting spectrum consisting of a weak comp near the pump frequency and Stokes Raman-assisted optical frequency comp with a soliton-like spectrum in the enamel dispersion range. This is frequency, not wavelength as in the previous slide. The experimental details can be found in our paper. Note that previously a very interesting regime was discovered in the group of Kerr and Raman. The Stokes soliton was formed by optimizing its Raman interaction in space and time within an optical potential well shared with dissipative Kerr soliton generated with a pump in the anomalous dispersion range. But our regime was not a similar regime compared to Stokes soliton coexisting with a bright dissipative soliton, because we pumped a microresonator in the normal dispersion range, not anomalous. So here the motivation of theoretical work was to explain our experimental spectrum. Then numerically simulated stable spectrum and spectral envelope of the Raman-assisted comp are plotted here. We chose detuning and the pump power to attain a sufficiently good agreement between the simulated and experimental spectrum. The simulated intensity distribution in the time domain is shown here. Next, we filtered out the Raman-assisted comp in the spectral domain and found its field distribution in the time domain. The temporal intensity and phase of a Stokes Raman-assisted soliton are presented in this subplot. we indeed obtained the soliton. This solution has an almost flat phase, spectral and temporal, and its duration is 180 femtoseconds. A time bandwidth product is 0.315 as expected for solitonic pulses. So we demonstrated a novel regime of Stokes soliton formation with a pump in the normal dispersion range without formation of a bright dissipative soliton near the pump frequency. A good agreement between numerical and experimental results is achieved. And in the similar scheme, but with another experimental settings, we obtained experimentally Raman-assisted nested combs in two different mode families.
So, Elena, sorry for interrupting. So the question regarding the previous slide, maybe two slides before. So you mentioned in the previous one. Yeah. So you mentioned that you compare two situations. First, you simulate the full system, and then you do the simulation without Raman response. Does it mean that you include all nonlinearities except for the Raman susceptibility?
Yes, Kerr linearity was full in both cases, but here Raman response was switched off, and here it was switched on. But dispersion and another effects was identical. So in these equations, when the Raman function was switched on, FR is equal to 0.18, but for the second simulation situation, when we switch off Raman, this was 0, but other terms are similar.
All right, thank you.
Okay, let me continue. Here we can see Raman-assisted nested combs into different mode families with soliton-like.
No, I'm sorry, I'm not very familiar with the terminology. What meant by nested comb?
Okay, you can see that the spectra one into another. So we see that they not separated in spectral scale. So this one red belongs to transverse electric mode families, but another soliton belongs to transverse magnetic mode families, and this term means only this.
So the different polarization, different polarization overlap spectrally.
Yes. The pump wavelengths without component nearby was in the normal dispersion range, and these combs are generated in the anomalous dispersion range. We approximated the envelopes of the experimental parts of the spectra belonging to mode families by hyperbolic second shape. And after that, assuming that this Raman spectra in the time domain correspond to the Fourier transform limited pulses, as should be for solitons, we obtained hyperbolic second temporal intensity profiles with pulse duration shown here. The numerical simulation in the framework of the coupled Lugiato-Lefever equation confirms that the combs are soliton. And now let's speak about nonlinear effects in chalcogenide microspheres, namely about Raman lacing. To date, multi-mode Raman lacing in chalcogenide microresonators was obtained in a few works. Potentially, Raman generation in chalcogenide microspheres can be obtained in the mid-infrared range, which is inaccessible, for example, for Silica microresonators. However, even in the telecommunication range, chalcogenide microspheres made of arsenic sulfide glass can have certain advantages. It is possible to obtain Raman lacing in the L band with a C band pump due to the maximum of Raman gain function corresponds to 10 terahertz. But for Silica glass, the Raman shift maximum is about 13 terahertz. Raman lacing was attained in a sample with a diameter of 34 microns and Q factors of 1 million. Here the experimental setup is shown. Then the pump power excess of the threshold was not very high. We attained a single mode Raman lacing with a more than 50 nanometers wavelength tuning achieved solely by a pump wavelength tuning. It was the first demonstration of a single mode Raman lacing in a chalcogenide microsphere. Details can be found in our paper. Previously published Raman microlasers were multi-mode. We also performed the numerical simulation of the Lugiato-Lefever equation for quality of understanding of Raman lacing. We obtained a good agreement between the experimental and theoretical results. And then the pump power significantly exceeded the threshold. Raman lacing became multi-mode, and different module families were excited. Moreover, cascade processes were observed. In cascade processes, under the action of a continuous wave pump, initially the first order Raman radiation is generated, which serves as a pump for the second order Raman radiation. Then the second order Raman radiation pumps the third order Raman radiation, and so on. As the optical spectrum analyzer operating range is limited by 1.7 microns, the measurement scheme was modified to detect optical spectra beyond 1.7 microns. For this, we use a detector together with a scanning grating monochromator integrated to the computer-controlled scheme. For the pump wavelengths of 1.57 microns, we attained 4 orders of Raman lacing. The maximum Raman order of 4 was located at 201 microns. And further, let's move to tellurite microresonators, in which not only nonlinear optical but also laser processes are implemented. Let's continue the topic of Raman generation. Tellurite glasses have huge values of the Raman gain, which are 2 orders of magnitude higher than for Silica glass, and the maximum of Raman gain is located at about 20-28 terahertz against 13 terahertz for Silica glass. In addition, a characteristic feature of the Raman response function is the presence of 3 maxima. For the used tellurite glasses, the highest gain has a maximum at about 22 terahertz, and a maximum at about 27 terahertz have a comparable value. Therefore, tellurite glasses are promising materials for implementing frequency conversion based on simulated Raman scattering. Raman lasers based on tellurite fibers are well known, but the implementation of Raman lacing in tellurite microresonators has not been previously reported. One of the reasons is rather low quality factors. We achieved a record loaded Q factors for tellurite microspheres. The previous record was in 2.5 times lower. We obtained Raman lasing in a tellurite microresonators for the first time for this type of resonators. The simplified scheme is shown here. Using the same C-band telecom pump laser, we attained 2 orders of Raman lasing at the longest wavelengths, slightly beyond 2 microns. And here we consider another process. Simulated Brilliant scattering is a process of scattering of light wave on hypersound wave, which may lead to generation of Stokes wave at low frequency with low phase noise and narrow line-wise compared to the pump wavelengths. The Brilliant shift depends on material properties. This is of order 10 gigahertz for glasses. Since this value is much smaller than FSR of microspheres, Brilluen lasing occurs in different mode families. The schematic diagram of Brilluen laser is shown here. The pump wave initiate the generation of backward Stokes Brilluen wave and acts as a pump for the Stokes, the first order Brilluen wave acts as a pumps for the second cascade. The second order Brilluen wave propagates in the opposite direction with respect to the first order wave. Further, the second order Brilluen wave pumps the third order Brilluen wave, and so on. In this case, even order Brilluen waves propagates in the forward direction, while odd order Brilluen waves propagates in the backward direction relative to the pump. We used the tellurite microspheres with a diameter of 75 microns. Here you can see the data from the oscilloscope I showed.
Elena, sorry, is this kind of a behavior of odd and even modes propagation? Is it obvious? I'm not just.
For Brilluen scattering, this is pump wave, and the Brilluen wave propagates opposite the pump.
Mm-hmm. But some of them propagate along in the same direction as the pump.
The even odd in the same direction, and the odd order in opposite direction.
Yeah, but why does it happen?
Because the features of scattering of light on sound wave. It's scattered in opposite. So pump initiate hypersound wave, and after that the light scattered in this sound in opposite.
Is it like adding even or odd numbers of reciprocal vectors from the lattice?
Sorry.
So the block vectors. So is it adding even numbers?
Yes.
Or odd numbers of block vectors?
Yes.
Okay, maybe just I need to go into more details on that. Okay, maybe we can discuss afterwards. All right, thank you.
In our scheme, we can see only even order Brilluen waves, and the resolution of optical spectrum analyzer was 0.02 nanometers, and the wavelength accuracy made it possible to identify different Brilluen cascades and measured the Brilluen shifts, but did not allow accurate measurement of the individual narrowband spectral line shapes of Brilluen lasing. By tuning the pump laser wavelengths, we observed a spectrum of generated Stokes Brilluen waves of the second order here wavelengths, here frequency, and fourth order here wavelengths and here frequency. And to explain experimental results on Cascade Brilloin lacing, we developed a theoretical model using the mean field model and the coupled mode theory. The equations are the following, and the meaning of symbol is explained. We considered steady state processes, and the system of equations describing Cascade Brilloin lacing became algebraic. For the successfully analyzed n, where n is the maximum order of the generated Brilloin cascade, the system easily solved analytically, and expressions for Brilloin powers and thresholds pump powers were found. Theoretically calculated diagrams demonstrating the number of Brilloin laser cascades depending on the pump power and detuning. The Q factor and detuning significantly affect the number of generated cascade. Indeed, to generate higher order cascade Brilloin waves, a large Q factor is required. So the calculations confirmed that the experimentally attained first order Brilloin lacing was possible due to the record high Q factors of the produced microspheres or microresonators made of tellurite glasses. Next, we study lacing in rare earth ion doped tellurite microsphere. Let me consider the simple case of in-band pumping, which was implemented in thulium doped and erbium doped samples, and start from theoretical analytical method. The rate equations for the population density are the following. The evolution of time-dependent intracavity amplitude inside the microsphere are described by the coupled differential equations. These equations are written for all modes from the gain bands. The full model, which can be used for not only in-band pumped microlasers, but also for microlasers with multicolor lacing in scheme with several energy levels, is described here. But this system contains a lot of coupled equations corresponding to the number of considered modes with eigenfrequency in the gain bands. Its dynamics can be studied by direct numerical integration starting from noise initial conditions. After a long enough simulation time, after decay of relaxation oscillations, the system tends to the equilibrium state. However, this method is very time consuming if used in many realizations for different parameters of the systems. We proposed an analytical method allowing us to solve this system with allowance for remote competition and find a stable continuous wave solution. Our approach allows solving only a single nonlinear algebraic equation, but many times using exhaustive search for each eigenmode for single color generation. We obtained this analytical solution for intracavity powers. After that, only physically meaningful, stable solutions were chosen. For verification, the Runge-Kutta method is also used. We obtained a good agreement with the solutions obtained by our method, but note that the Runge-Kutta algorithm is executed much longer. And this slide demonstrates the numerical and experimental results for in-band pumped thulium microlasers. Here, the gain function is plotted. The wavelengths corresponding to the maximum of the gain depends on the population of the upper laser level N2 and determines the generated wavelengths. Our model gives that the expected laser wavelengths with allowance for mode competition depends on thulium ion concentration and Q factors and does not depend on microsphere diameter and pump power. The increase of Q factor, the laser wavelengths grows smoothly. The higher the concentration and Q factor, the longer the laser wavelength. Laser threshold depends on Q factors and a microsphere size. This figure demonstrates that for a certain active ion concentration, the larger the microsphere diameter, the higher the threshold pump power. We also performed the experimental study according to this simplified scheme in a thulium-doped microsphere with a diameter of 320 microns. These are views from two CCD cameras. For a Q factor of 1 million, we attained LS generation at 1.9 microns, which agrees with the theoretical prediction on this point. The experimental details are published. Further, we studied lasing in erbium-doped in-band microsphere. This is a calculated gain function for different population density of the upper laser level. Note that the wavelength at which absolute maximum gain is obtained, marked by black circles, contains jumps. Then population change slightly. This fact is the main reason of the lasing wavelength jumps, which is shown here. Here the expected laser wavelengths for different Q factors. Here we can see that the threshold is function of Q factors for different microsphere diameters. The qualitative dependencies of these graphs is the same as for thulium. The experiments were also performed. This is a view of a produced microsphere using a microscope. This spectrum demonstrates whispering gallery modes, and these are views from two CCD cameras. Green light is due to upconversion energy transfer processes. For a low Q factor, we attained lasing in the C band, but then we increased the total Q factor by regulating the distance between a microsphere and a fiber taper. The laser wavelength jumped to the A band, as was numerically predicted. And in summary, recent achievements of our team concerning theoretical and experimental investigation of silica, chalcogenide, and tellurite glass spherical microresonators pumped in C band were presented. And this table summarized reported results. Thank you very much.
Thank you, Elena. Interesting talk. So we have some time for questions. Colleagues, if you have any, please raise your hands. So in the meantime, I will start with the first one. So somewhere around slide number 19, you discussed the generation of higher order Stokes components. Yeah. So I wonder how far can you go? So is the fourth order is a maximum, or you can go even to higher orders if you adjust somehow the scheme?
In our scheme, the maximum was fourth order, but the Q factor for microsphere used in these experiments was 1 million. Now we significantly improved our method for producing of soft glass microresonators, and we hope to obtain experimental samples with high Q factors, and we predicted in numerical simulation that for higher Q factors, we will obtain Raman orders up to maybe 6 order, since chalcogenide glasses are transparent in the range beyond 2 microns, but silica fiber taper is not very well transparent. We will use taper based on other, not silica glass, and we are planning to conduct experiments with chalcogenide microsphere with high Q factor and with fiber taper made of chalcogenide or maybe tellurite glass.
Right, right. Thank you. So I do not see other questions from the audience in the chat or in the Zoom. So I guess we can resume. So maybe a couple of words about further plans, so further experimental research. So you mentioned that you're going for higher orders. So responding to the previous question, maybe some other ideas.
Yes, we are planning to move to the range beyond 2 microns with tellurite and chalcogenide microspheres. We are planning to investigate optical frequency comp generation in soft glasses microsphere. Here you can see that today we have no comp generation in chalcogenide and tellurite glasses, but we are planning to do this soon.
Okay, thank you. And then a small question just to educate myself. So as far as I know, this 155 micron is important wavelength for telecom.
Yeah.
And, do I understand correctly that this is related to the fact that we have almost zero dispersion around that wavelength? Or it's just the issue of losses, how people chose that wavelength?
For telecommunication, this means that losses are minimal at this wavelength at 1.55, and our studies we have some applications of our comps generated in Silica microresonators when we generated optical frequency comps in resonators and FSR between lines of 400 terahertz. After that, together with our colleagues from the Institute of Telecommunication, we started the possibility of using these comb lines for passive networks, and such experiment was conducted by our colleagues.
Right, thank you. There is another question from Ilya Vatnik. Ilya, please. You can unmute yourself and switch on the camera.
Okay, thank you very much. Thank you, Elena, for the very interesting talk. I've got a question about your erbium doped microspheres. I guess like 26 or something. Yeah. So this slide, the picture B, image of the fabricated erbium doped microsphere. So you first manufactured a fiber with cladding doped with erbium ions, or you just made a preform and right after that prepared your microsphere?
For microspheres,
Yes.
in principle, we can use core cladding fibers, but it's more convenient to use single index fiber without core and without cladding. This is a filament made of a glass of one sort.
Okay, so it's a homemade preform.
Yes, this is not preform. Yeah. It was made as it was rasplav, melting of glass, and after that a filament was drawn. It's not preform. It's more simple for this case. It was this filament was made in the Institute of Chemistry, and then the glass was prepared. It was softened, and after that it was drawn. It was not very long. It was about maybe a few tens of centimeters. And for another experiments, of course, so we can use core clad fibers and produce the similar devices.
Thank you. And the second part of probably the same question. While preparing these microspheres, have you met any issues of diffusion of active ions from the boundary to the towards the center of the sphere? I mean, were there any problems with decreasing of the active ions density at the boundary of microsphere or not?
We did not study in detail this question, but I believe that this is not very important since the glass is homogeneous and
yes, but I'm sorry, but you melt this, you melt it, and when it's melted, one can think about diffusion of the active ions to the place. Okay, it's okay. I got no. I'm sorry. Yeah, you're absolutely right. Yeah, there should be no problems with diffusions. Yes. Okay, thank you. You're right.
Thanks, Elena. Thanks, Ilya, for the question. So I guess we are through with questions. So I would like to announce.
Maxim, sorry. Yeah. Can I also ask a question?
Yes, please, sure.
My question is just kind of probably obvious for some, but the question is the following: how can I distinguish the Raman scattering and Brillian scattering during the experiment? Is there just a difference in frequency or something else?
Sorry, in this for this slide for Brillian scattering, we experimentally changed the pump wavelengths, and after that, then we experimentally go to the suitable resonance. We attained these effects, and in the case of Raman generation, I believe that we work with higher Q factors, and maybe I don't understand your question.
So if, for example, I observe some kind of non-elastic scattering during the experiment, and I don't know is it actually Brillian scattering or Raman scattering, how can I distinguish them? Or probably
okay.
I just they are usually observed in different systems.
Yes, for Brillian scattering, the shift is about 10 gigahertz. You can see here pump wavelengths at 156.4.9 nanometers, and here you can see the second and the fourth order. But for Raman scattering, the distance between pump and Stokes components is much larger. Here, the distance is about 27 terahertz. It's not a problem to distinguish them. And indeed, then we done experiments. We can simultaneously obtain and Brilluen and Raman scattering.
Okay, thank you.
Good. So very interesting discussion. Thank you, Pasha. Thank you, Elena. So in the meantime, I would like to announce the next seminar, which will be given right in a week by Dr. Ksenia Chichai, who comes from Immanuel Kant Baltic Federal University, on the dynamic of topological magnetic solitons from domain walls to skyrmions. So stay with us and see you next time. Goodbye.
Thank you. Goodbye.
Thanks a lot.